Let's talk about L'Hopital's rule. So really in our textbook there are two parts of this rule. They call it part 1 and part 2. But they're pretty much telling you to do the same thing. So what I have here on the screen is kind of those two parts smushed together as one rule. So there are a lot of conditions that can seem a little bit overwhelming, but they're most often met. So the situation is going to be something like this, where you have the limit of x approaching something, and then some sort of ratio of functions. So some sort of f of x on top and a g on the bottom. So f and g both need to be differentiable. They need to actually have derivatives, at least like where it matters, right? So wherever this limit is happening, they have to have derivatives in that area, which is not something that we have to worry about very often. So a, this is the number that x is approaching here. It's either a number, and it can even be a one-sided limit, or it can be one of the infinities, so positive infinity or negative infinity. So this rule pretty much works for every type of limit that you might see. And then the last condition that we have to at least notice here, even though it's not something we'll have to enforce very often, is that g prime should not equal 0. And I said where it counts here. So what I mean is that coming up in our rule, we're going to be dividing by g prime. So if this is 0, like all around A, or if x is approaching infinity, like if it's 0 for like a long stretch, then technically this doesn't work. But again, these things pretty much are always going to happen, so don't worry about the conditions quite so much. If there's a problem area, it'll probably show itself in a different way, where either you won't be able to take the derivative, or you can't plug the correct number in, or you are dividing by 0. Okay, so in that case, if you have the limit as x approaches whatever of this ratio, if it comes out to be an indeterminate limit of the form 0 over 0, meaning f and g at a both go to 0, or positive or negative infinity over infinity, right? So both of them go to, one of the infinities. It doesn't have to be the same one, so one could be positive, one could be negative, and it would make it a negative infinity over infinity. So if it's one of those cases, that makes it a limit that's much harder to compute. And we do have some rules already from Calc 1 for how to deal with a limit like this, but pretty much just for rational functions, otherwise we're kind of out of luck. So in any of these cases, you take your limit, and it will be equal to the same limit, but instead of f over g, now we have f prime over g prime. So you take the derivative of the top, the derivative of the bottom, and then essentially try again. See if, now that you look at the derivative, see if it's something that you can, compute the limit of on its own. It's worth pointing out here, before we do 2 examples in this video, that this expression right here is not the derivative of f over g, right? The derivative of f over g altogether would require the quotient rule. So what we're doing is kind of like the thing you're not supposed to do for the quotient rule, right? We just took their individual derivatives. So this is a slightly different thing than just differentiating the entire function. We're doing it in pieces as like a ratio. Okay, so let's actually see L'Hopital's rule in action. I have 2 examples for this video. You can see them on the screen here. Sine of x over x. It's the first example in the book because it's a classic L'Hopital problem. So when we have the limit as x approaches 0, our first instinct is probably just to plug in 0, right? If I can plug this number in, I'm probably good to go. But we run into issues when we do that for this particular limit. So you would have the sine of 0 on the top, and then straight up 0 on the bottom if we plugged it in. The sine of 0 is 0. So what we have is a 0 over 0 limit. And we actually got literally 0 over 0 when we plugged it in here, but it just has to be kind of headed in that direction for it to be a 0 over 0 type. So what that tells you, since both of these pieces are differentiable everywhere, so that part's good, what that tells you is that L'Hopital's rule applies. So what we can do is look at the limit of the ratio of the derivatives instead. So I'm still going to have x going to 0. That part just copies over. Now I'm going to take the derivative of sine, which is cosine. And then the derivative of x is 1. That's what L'Hopital's rule is telling us we can do. The limit of this ratio is the limit of the ratio of their derivatives. And then you try again, right? It's a whole new limit problem. So we think, okay, phase 1, can I plug in 0? And in fact, in this format, you can, right? You would just have the cosine of 0 over 1. And the cosine of 0 is 1. So our answer here is just 1. Okay, let's try it again in this second example. So here I have a one-sided limit, right? We have the limit as x approaches 0 just from the right-hand side. That little plus sign right there is telling you just the positive side of 0, not the negative side. It's not going to affect anything that you actually do in this problem. You'll compute it and kind of ignore it the whole time. The reason that we have that 0 there is because ln of x is in this problem. And ln of x, its graph, looks like this. Oops, there we go. This is the graph of ln of x, right? So it crosses the x-axis at 1 and then has this vertical asymptote that plummets down at x equals 0, and it doesn't exist on the other side of 0. So if we're talking about this function and then its limit at 0, you always see that little plus sign there because otherwise it's a DNE, but like a cheap DNE. So we just say like, okay, only focus on this side. Okay, so now we think x is still going to some sort of number, so can I plug that number in? We would have the ln of 0, which doesn't exist, and then 1 over 0, which also doesn't exist, but I'm just thinking about where these things are headed. Now this, as I plug in numbers really close to 0 on the ln graph, right, like plugging in x values here and here and here and here, their y values are plummeting south towards negative infinity. And then 1 over 0, again, we can't actually compute that, so I'm doing the limit of 1 over x squared as x squared goes to 0, really. But this is 1 divided by tiny, tiny, tiny positive numbers, which is going to be a really big positive number. So this denominator goes to infinity. So I would say this limit is a negative infinity over infinity form, which again means, since both of these are differentiable on their domains, that L'Hopital's rule applies. So I'm going to do the same thing that I did in the previous example. I'll take the limit of the individual derivatives as a ratio and see if that helps me solve. Okay, so again, I copy the same limit as x approaches 0 from the right. The derivative of ln of x is 1 over x. 1 over x squared, for derivative purposes, is x to the negative 2. So its derivative is negative 2x to the negative 3. So as this is, it looks kind of messy, so we're going to clean this up. So we have 1 over x over negative 2 over x cubed. So what I'm doing here in my scratch work is just taking this x to the negative 3 and making it an over x cubed. Dividing by a fraction is like multiplying by its reciprocal. And we get some cancellations. We get x squared left on top and then a negative 2 in the bottom. So I'm going to take one more step here. So in this step, I actually took derivatives. I used L'Hopital's rule. Here, I'm not actually doing anybody's derivative. I'm just simplifying what I have. I just have x squared over negative 2. And just like the previous problem, we go, oh, that's something I can just plug 0 into. 0 squared over negative 2 is just 0. So this same method works. So both of these had a 0 in them, kind of as a coincidence. But this same method works if x is approaching infinity, or any different number.